Let's take a look at this example. Example 2.3, Laplace transform solution of the differential equation. This is the example from the book, but the book says all initial conditions are 0, but I made a slight change. Okay, so now we have those initial conditions. So we need to use the Laplace transform. And the handout equation sheets, we have those of the two Laplace transform of the differential equation. For the first one, s squared y of s minus sy of 0 minus y prime of 0. This whole thing is this. And then plus 12 sy of s minus sy of 0. And then plus 32 y of s equals, what's going to be on the right-hand side? 32 times u of t. So make sure we want to put 32 times u of t. Laplace transform of u of t, that is 1 over s, right? You need to build a habit of making parentheses for double prime and single prime, because if I give you 1 or -1 in front of this second order differential equation, then you need to multiply whatever the constant into all of these three, just like what we have here. Now I'm going to collect all the ys terms. We have here, here, and here. Actually, before we do that, let's apply the initial condition. Y of 0 equals to 0. Y prime of 0 equals to 1. I'm sorry, this should be no s in here. Then we have s squared plus 12s plus 32. That's the y of s term. Equals, we have 32 over s. And then we have plus 1 right there, because y prime of 0 is 1, and that's the -1. Move it over to the other side. That's the positive 1. Combine these two, and s plus 32 over s. Then y of s equals s plus 32 over s times 1 over s squared plus 12s plus 32. Now we need to do the partial fraction to separate these two. Y of s equal a over s plus, is this factorable? So we're going to do b over s plus 4 plus c over s plus 8. And then for the numerator, if you combine them all, we're going to have s plus 4, s plus 8. Numerator, a, s plus 4, s plus 8, plus b, s plus 8, plus c, s plus 4. So the numerator, s plus 12, should be equal to the numerator right there. So what we did in the last example, we distribute all of this and compare s squared term, collect all the s squared terms and s terms and compare with the s plus 32. We can do that. However, for this time, since we have all these three different numbers, here's another technique that we can do. I'm going to write one more time here. S plus 32 equals as plus 4, s plus 8, b times s plus 8 plus c s plus 4. So what I'm going to do, I'm going to substitute different s values in here. So I'm going to pick, if we let s equals to -4, then on the left-hand side, it's going to be 28. And this term is going to be 0. This term is going to be 0. We only have b terms, b times -4. And when you plug -4 into s, it's going to be +4. So from here, we have 28 equals 16, negative 16b. We have b equals negative 28 over 16 equals 7 over 4. Now the second number I'm going to use, we let s equals to negative 8. And then when you plug in negative 8 on the left-hand side, we have 24. And then right-hand side, negative 8. This term is going to go away, and this term is going to go away. C terms is the only one we have. C times S, negative 8. And when you plug in negative 8 here, it's going to be negative 4. From here, 24 equals 32. C equals 24 over 32. That is 3 over 4. The next number we can use is 0. So if you let S equals to 0, then the left-hand side is going to be 32. Right-hand side, this term is 0, this term is 0. A term is the only one. 8 times 4 times 8. From here, 32 equals 32a. A equals to 1. Then we have y of s equals a is what? 1. B is what? Negative 7 over 4. C is what? 3 over 4. Then we take the inverse Laplace transform. Then y of t equals 1 minus 7 over 4 e to the negative 4t plus 3 over 4 e to the negative 8t u of t. We talk about the transfer functions, right? In the beginning of the first class, we have input r of t, output c of t, input as a reference to input. That's why we want to use r, and then control the output. So we want to use c. And then the middle box is what we want to have it to transfer function. So that transfer function in the middle box is going to be output over input. And we're going to call it g of s. So g of s is the transfer function. And that's the output over input. Therefore, it's going to be c of s over r of s. We take the Laplace transform of this as c of s plus lowercase c, that should be c of 0, plus 2c of s equals r of s. And then if you combine these cs terms together, we have s plus 2 c of s, and then c of 0 is 0, and we have r of s. And the transfer function g of s, c of s over r of s. Therefore, it's going to be 1 over s plus 2. Next problem is the same, but this time we have r of t is given, okay? And then ask us to find the system response c of t. Let's find the c of t. So I'm going to multiply both sides by rs. C of s equals 1 over s plus 2 times r of s. R of t. R of t, lowercase. R of t is given u of t. I can give you something else, right? R of t as a 1, R of t as a t. So what we need to do, you need to find R of s based on what you are given as a R of t. So if you take the Laplace transform of R of t, it's going to be R of s, and u of t is what? 1 over s. Thank you. You put in 1 over s plus 2, 1 over s. Now we need to do the partial fraction again. And when you do the partial fraction, you do it. It's going to be negative 1 over 2, 1 over s plus 2, plus 1 over 2 times 1 over s. So take the inverse Laplace transform from here. Now we have C of t equals negative 1 over 2 e to the negative 2t plus 1 over 2 u of t. We're going to look at three different systems in this chapter. The first one is the circuit. Second one is a transitional mechanical system. Third one is a rotational mechanical system. We're going to work on inductor, capacitor, and the resistor. So all this table is given, so you don't have to remember any of those, but you need to know how to use them. First, simple one loop circuit. We have inductor, resistor, capacitor. And the first example, what we're gonna do, we're gonna use voltage current column, this guy. So when we do KVL around this loop, I of t is going into negative terminal of V of t, therefore negative V of t, L for inductors, okay, L di over dt, and for resistor, R times I of t, and the capacitor, 1 over t integral I of t dt. And we don't have any pair for this integral for Laplace transform, right? So we have to do something about it. And we're going to use the definition of the charge, meaning I of t equals to dq over dt. So if you put this I of t everywhere, then integral times d over dt will cancel out. 1 over c times q of t going to be vc of t. So once we do that, we have this, and this is going to be v of t. Then using this v of t, we need to put that all in, and we need to reevaluate it. So if we actually work on it, we're going to use these two into this equation. Now we are getting into this. Don't copy down, just watch this. We're going to actually do this exact same example using numbers. So we have a VC of t and all of this. Now we can use Laplace transform. Okay? So it's a double prime, so s squared VC of t, s VC of t. And then initial conditions, if we assume the initial conditions are all 0, we end up getting this. And then put it into form. That's going to be the answer. Let's do this. So exact same circuit, but we're going to use the actual number I of t in that direction. Then negative v of t plus L. Now it's going to be 2 di of t over dt plus 10 times I of t plus 1 over c q of t, and then c is 1 goes to 0. And also we have I of t equals dq over dt. So we're going to substitute this guy for here. That 2 times d squared q of t over dt squared plus 10 dq of t over dt plus q of t equals v of t. Our transfer function that we need to find is given as a vc of s over vs. We have a v of t. When you take the Laplace transform of v of t, it's going to be v of s. However, we don't see any vc of s. However, we have this relationship. Therefore, anywhere you see q of t, we can just simply replace with the vc of t. Then take the Laplace transform of that. All the initial conditions are 0. So we have 2 times s squared vc of s. That's the only term. Plus 10s vc of s plus vc of s equals v of s. Factor out vc of x, 2s squared plus 10s plus 1. Vc of s equals to v of s. Our transfer function g of s equals to vc of s over v of s. Therefore, we need to have 1 over 2s squared plus 10s plus 1. So that's our transfer function. Final answer should be, we divide top and bottom by 2, then s squared plus 5s plus 1 over 2. So this time, the same circuit, but we're going to use this. I want you to highlight your handout, okay, equation sheets. Okay, highlight this portion. So this is first and last time we're going to tackle circuit problem using differential equation. From now on, we are not going to do that since we have a shortcut to get to this transfer function much quicker while we go through all of this, right? So highlight this, and then it says impedance Z equals to Vs over Is. So this guy is gonna act as R. So whatever we wanna find the voltage across the circuit, this times I, this times I, this times I. Make sense? That'll give us the voltage. Okay, so typically we call in the circuit, these are the Z terms. The later chapter 7 or chapter 8, when we get into first order, second order, get transient system, we call Z. And when you have something like this, we can combine them. We let this as a Z1, Z2, Z3, and so on. So we have same circuit. Now we're gonna use that column. So I'm gonna use the same notation that what we did in our circuit class. Z for L, for inductors, it's going to be SL. Z for capacitor equals 1 over SC. Just keep that in mind. And we're going to write the KVL directly in terms of S domain, like a frequency domain. Same thing, negative V of S, getting into negative terminal, so it's a negative, plus ZL, which is 2 times S times I of S, V equals IR, right? V equals I times Z, and then for resistor, 10 times I of S, capacitor, plus 1 over SC, which is 1, times I of S equals to 0. And we need to find VC of S over VS. We need to have a V of C. But we know VC of S equals Z times I, right? So 1 over S times I of S. That's the voltage across this capacitor. This whole thing is VC of S. And also from here, we can say all I of S equals to S times VC of S. Now we're going to put that into here and here. Then 2S squared VC of S plus 10S VC of S plus VC of S equals to V of S. Factor out VC of S, 2S squared plus 10S plus 1. VC of S equals to V of S. Same thing, VC of S over V of S. 1 over S squared plus 5S plus 1 over 2. So we get to the same answer. This is what the VL of S, the voltage across this inductor. That's the formula, right? And then this is the voltage across the resistor. And this is voltage across the capacitor. That's too easy, right? One loop circuit is too easy. For the exam and the quiz, you're not going to see one loop. So minimum 2 loops. So something like this. Now we need to use mesh analysis and nodal analysis. Yay! So basically what we want to do, we want to have one equation using mesh current here. second equation from mesh current here. And then we're gonna organize in terms of I1 and I2. And then we're gonna use Cramer's rule. I'm gonna say I1 and then I2. So in mesh 1, we are doing the mesh analysis. So we have negative V I of S plus 5I1 of S plus, what's the Z of inductor? LS. L is 2. S. So that's the Z. And then we need to multiply this times the current. But these are the mesh current. They are not going through this guy. So we need to write, this is the reference to I1. So I1S minus I2 of S equals to 0. And then let's say we combine I1 terms together, 2S plus 5, I1 of S minus 2S, I2 of S equals to B, I of S. That's our first equation. And the second equation is going to be starting from 10 times I2 of S plus 1 over SC, 1 over 5 I2 of S plus LS 2S I2 of S minus I1 of S equals to 0. So if we collect I sub 1 terms, there's only one, negative 2S I1 of S plus S2 terms, 10 plus. This is 1 over S over 5. So it's going to be 5 over S, 10 plus 2S. Okay, so now we're going to use Cramer's rule. So the delta determinant of the coefficient of I1 and I2 from first equation, 2S plus 5, negative 2S. Second equation, negative 2S. And if you have the common denominator as an S, we have 2S squared plus 10S plus 5. That is AD 2S plus 5. 2S squared plus 10S plus 5 over SAD minus BC for S squared. And then we can do delta 1 and delta 2 to solve that. The capacitor is associated with the second current I sub 2. So in this case, we don't have to find delta 1. We're going to just find the delta 2. For the delta 2, first column is the same. And then second column is going to be right-hand side of the equation, which is VI of S, or 0. AD 0 minus BC 2S times VI of S